you guys cooking yourself, right? So you must be good at making something like dumplings. Because for me, that mooncake is almost the same with dumpling. You just wrapped something with flour pasta, right? Something like that. So a lot of Chinese food is actually the same. Right. So you have 11 today?
Yes.
Wow, what a big surprise for me. What's your name? I never see you.
The newcomer.
What's your name?
Shenyang.
You are Shenyang. Right, what happened to you for the last maybe 3 weeks?
No,
You didn't show up?
1 week.
1 week? This is the 3rd week.
No, the first week I was there.
But this is the 3rd week. Yes, we definitely have class last week and the 1st week, right? So this is the 3rd week.
Other than the second week,
So what happened to you?
I first thing I check up for doctor.
Do you ask for absence with Vivian or John?
Yeah, but
You did?
yeah.
All right. I hope that every of you, we have 11 students for this semester for soil mechanics. I hope that you all attend the soil mechanics class, okay? Because the performance accounts for almost 40% of your final score. Nothing else, just help you to pass the examination. Because for next year, we have no international students for civil engineering. So if you didn't pass the examination and the makeup examination, you didn't make it, then you have no chance. You have no chance to learn soil mechanics again, to go to the points. I don't know what it's called, but points. And finally, it will influence your degree because you didn't finish the study actually. So you guys actually a little bit different, in a little bit different situation with last grade, right? So just grab the opportunity to get the score for the performance part. So in chapter 3, we talk about some weight-volume relationships. So actually, finally, after study of this chapter, what you learn is just some equations, some relationship between density, volume, weight, or mass, something like this. You may think it's not important, but this chapter is a very, very basic chapter for you to learn the mechanical property of soil. And we can actually spend only one class to tell you the relationship. But in here, it's better to let you know how we got those relationships, right? And then if you have no tables without any help, then you can still with some very, very basic relationship and then try to find or try to drive out some complex relationship yourself. And we talk about 3 main volume relationship first, void ratio, porosity, and degree of saturation. You see, these are all based on volume ratio, right? These are 3 main volume relationship. And then we talk about some weight relationship. 2 main weight relationship. The first is moisture content. You see, this is the ratio between weight or between mass and unit weight. Unit weight, when we say unit weight or density, it's the ratio weight relationship. Based on those 5 main volume weight relationship, then we drive out some complex relationships. The first is to introduce the unit specific gravity, and based on this, we drive out the unit weight, some unit weight relationships. For example, this and this. And based on this too, we got this one. And I think we stopped here. We stopped here in last class, right? You confused or not? Clear, still clear with this, because we haven't meet for almost 1 week. So the basic volume relationship, basic volume or weight relationship, that's simple. We want to repeat it. But from here, we introduced the specific gravity. The specific gravity was that it is actually based on the weight of water, the unit weight of water, right? That means for the same volume of soil, how much of the weight compared to the water. This is the ratio. This is GS, specific gravity. So WS, S in here is solid. When you see S in here, that is solid. If you see W, that is water. For water, we know that soil has 3 phases, right? And if it is A in here, that is air. And if it is V in here, that is voice, right? So keep in mind about this. So the weight of solids, that is the weight of solid particles, is actually the products of specific gravity and the unit weight of water. So based on this, and we know that we have this, right? Water content, that is the first weight relationship we learn. That is the weight of water to the weight of solid, right? And we know that the basic volume relationship, that is void ratio, it is the volume of voids to the volume of solid, right? So the bottom one is always the solid volume or the solid weight. So in here we have this, right? And so we have weight of water equals to the products of these two, right? The weight of solids multiply water content, that is in here. So we have this. And because weight of solids equals to this, so actually if you know specific gravity, we know that the unit weight for water is a constant value, right? It is a constant value. So as long as you know GS, you see you can calculate the weight of solids actually, and also with water content, you can also calculate the weight of water, right? So this is how to use GS. GS is much important even than void ratio and other parameters for soil. And so GS, because we have this, right? So this is how we calculate GS, but we never calculate GS. So this equation actually, I think is useless, because when we use GS, how we use GS, we usually measure GS with laboratory test, right? We usually got GS directly. We didn't use those parameters to drive out GS, but use GS to drive out WS, VS, or whatever, and other parameters. So you don't have to this relationship. You just know GS is what we should measure in laboratory. And based on GS, then we can calculate this and this. And this is GS. So let's see some unit weight derivations. So use the last two equations for weights of soil solids and water. We can derive the equation for moisture and dry unit weight respectively as follows. So this is gamma is unit weight, right? You know, unit weight is actually the weight divide volume, right? This is basic equation. And we know that for a soil, the weight is composed actually three parts, right? But we think that there is no weight for air. So weight is the sum of solids and water, right? And the volume is still the total volume in here. And because in here, weight of solids and weight of water we can derive from GS. So in here, this part equals to this. And if we think the volume is void ratio E is equals to void ratio, so the total volume is actually 1 plus E. So this is for dry unit weight, the equation for dry unit weight. This is the first derivations from the basic equation in here for the unit weight. And we know that unit weight, but unit weight is not enough. Sometimes for soil, the unit weight is large, but the soil is not means that the soil is dense. Because the unit weight accounts for the weight of water and as well as the weight of solids, right? So if the soil is very, very, very weight, that means a lot of water contains in the soil. And this will induce also a very high unit weight. But now the soil, the unit weight is high. Maybe it is because the water content is high. Because the soil is weight, right? So in most cases, we design the embankment, we design the foundation. We use dry unit weight. We just use the solids part to calculate the unit weight. We call it dry unit weight. Dry unit weight, that is, we ignore the water part. We just calculate how much solids for a unit volume. This is easy, right? From here to here, it's easy because you put GS and gamma W out and put one plus W together. So this is easy. But dry unit weight, we know that dry unit weight is only account for the solids in here. And we know that the solids is this part. We can derive from the GS. So actually the dry unit weight can be derived with GS, with this equation. This is dry unit weight. Or we know that the relationship between dry unit weight and unit weight is actually, if you divide 1 plus water content in here, you got the dry unit weight relationship. This is why we have such a relationship. Because gamma D equals to this, gamma equals to this, or this. So the difference between these two is just from here to here, we divide 1 plus water content, right? So actually we got this, gamma D equals to gamma divided 1 plus water content. And from here to here, so if you put E out of the equation to the other side, then actually we can got this equation. This is easy, right? You just rewrite the equation again. Or you can, yes?
Sorry, how do you get the relationship between dry and wet?
In here. Oh. So we have this, right? That is gamma equals to we have this, and then we have gamma D equal to what's the difference between these two? What's the difference? So you have the same bottom, you have part same for the up part, right? So the difference actually, if you use gamma divided gamma D, you use this side divided this, and then again equals to this divided this. All of this part is the same. All of this part is the same. This divided this is just only equals to this one. So this is why we have gamma equals to, or you can say gamma D equals to gamma. Right? From here to there. Understand? No. Some of you lost. So this is two equations, right? This one is this. This one is this. No, this one is this, right? Now we got this. We got the derivation in the step. One by one, we have this now. And now, if we use the left part to divide, we if now I say that I use gamma divided gamma D, it is equal, gamma is this, right? Or gamma is this. Divided what? Divided this one, right? That is how you calculate this. The very basic way we learn in high school is multiply this part upside down, right? That is GS gamma W 1 plus E, right?
Right.
This is the same. So, and this part is the same. So finally what we got is that this equals to 1 minus omega water content, or 1 plus water content, right? So this is why we have this. But we didn't always write like this. We write we usually write in this way. Or we say that gamma D equals to gamma. This equation is very, very useful in your examination, in your homework. in later, if you learn a master, you're doing some laboratory test, this is very, very important. Why? Because without a soil, it's not always dry. You see, in the nature or in practice, the soil is always wet. But when we design the embankment, we design the foundation, we usually use dry unit weight. In laboratory, the most easiest, the easy way to get dry unit weight is use this equation. That is, unit weight is easy to got. You got a pound of soil, or you cut a block. You know its volume, right? You cut a block, the size, you know the volume, and then you know the weight. It's easy. You have a balance. You got the weight, the total weight and the volume. And these two parameters gives you the unit weight. This unit weight is the gamma, right? It's the weight unit weight. And the water content is also easy to get. You got, you got some container and you put some soil mass inside. This is the total mass. Remember that the water content equals to weight of water divided the weight of solids, right? So how to got water content? You have a certain mass of soil. For example, you weight for 100 grams of soil, you put in a container. Now you have the total mass, the total weight, right? You have the total weight. You put the container in the oven. Usually we drive in the oven for at least 24 hours. Let the soil dry enough. And then you get the mass, or you get the weight again. Now the weight is dry weight, right? That is WS. The initial weight is total weight. The final weight is solid weight. If total weight minus solid weight, that is the water weight, right? And you know the water weight, you know the solids weight. You got this with balance. You got this with this, right? And then you have this, you can calculate water content. These are all very basic and easy laboratory tests. You have water content and you have gamma. You have the unit weight, then you can calculate the dry unit weight of the soil. For example, you can go to a block 10 meters deep or 20 meters deep. You will find that the dry unit weight is different. Maybe the unit weight is the same, but because the water content change with depth, so actually dry unit weight is changing. So as well as for designation, we always use the dry unit weight to design. If you want to calculate a dry unit weight, this equation is the most used one. So this is how we derived derived this, and then from here to here is easy. We know that now gamma d equals to gs, right? So if you put this in this side, that is gamma d. Right? So again, 1 plus E equals to GS, right? And we put the 1 to this side. So this is this. So from this state to here, we can, as long as you know GS, you know gamma d, then you can derive an equation. derive all of them. So later I will post a table with all the equations. So then you will see it clearly. This is the first 3 derivations we got. And then let's see the degree of saturation, what we can get from here. We know this, right? We know that for the volume of water, the volume of water equals to weight of water divided unit weight of water, right? And what is this? This is what we got in here. So weight of water equals to the products between water content Gs and gamma W. So this is weight of water. This equals to here, and the bottom didn't change. So finally, if you know this, so actually volume of water equals to the water content, the products between water content and Gs. And because we know saturation degree is one of the basic volume relationship. It is the volume of water divided the volume of voids. That is how much of the water accounts all of the void volume, right? So as we know, we derived from here, we know the volume of water equals to this, right? And we say all of the derivation at very beginning, we say all of the derivation based on what? Based on, we think that the void ratio, the volume of void ratio is the voice volume, right? At the very beginning, we say why these two can be equal, because for a unit soil, it is actually the same. So finally, we got the derivation of saturation degree. As saturation degree equals to this, or we can write it like this, but it's usually write in this way, right? So now, if for a saturated soil, S equals to how much of S for saturated soil? How much of S for saturated soil? Yes, it's 1. Because you see in here, saturation degree, that is for the pore voids volume, how much of water inside, right? If all of the voids full of water, then it is saturated. That is, this two is already equal, right? The water volume equals to the voids volume. Then at this time, for saturated soil, S equals to 1. Then for a saturated soil, if S equals to 1, we have voids ratio equals to the products between water content and Gs, right? But this is only for saturated. Only for saturated soil. For any other soil, for a normal soil, didn't saturate it with this equation. We have this equation. So then let's see for saturated soil sample. Or what will change for the derivation, for those derivations? So again, saturated soil exists, or soil can be saturated when void space are completely filled with water. So for normal soil, this is a soil block. We have three phases, right? Solid, water, and air. But if a soil is fully saturated, that is, voids have no air inside. The void is full of water. We have only two phases now, just solids and water. So all the relationship from this photo will change to here, right? So if there is no voids of air, the weight relationship almost didn't change, but the weight relationship can be derived with some relationship included voids ratio or some other parameter related to volume. So actually some of the derivation will change. But of course, because the voids of air was ignored, oh yes, in here there is no air voids, so the volume relationship all change. Let's say, if we think that Vs equals to 1, that is solid, soil solids is 1, the volume for solids is 1, then this is void ratio, right? Right? This is what we derived all the derivation and all the relationship for saturation degree and for three derivations we talked about in maybe the last 2 or 3 slides. Why? Why we have this? Why we have this? Why we derived those relationships with this? Some of you may confuse that why you can write the voids, the total volume is 1 plus voids ratio. Let's say, because voids ratio, what is voids ratio? Voids ratio is VV to, what's the bottom? What? Volume of solids. Yes, it is volume of solids. This is a very basic definition of voids ratio, right? So now let's think for the Vs, we think it is equals to 1, right? We regard it is 1. We think that it is 1. Now just follow me. We think that Vs equals to 1. Then what is E? E should be equals to Vv, right? So this is Y in here. Vv equals to Vw equals to E. This is why Vs equals to 1. But why we can write Vx equals to 1? Because sometimes you got a block of soil, maybe it is 10 cubic meter. It can be any number. Why we would write it to 1? Because for such an equation, now if the total volume, the Vs is not 1, or it is 2, or the total volume, now we write it into 1 minus 1 plus voids ratio. If we say, because we drive out all the relationship is ratio, it doesn't matter if the total volume is 10 times or 100 times or any times. It doesn't matter because all the relationship, it is a ratio. So this is why we can use 1 in here. Just think, this is a unit or this is a unit. It doesn't matter because you say that the void ratio is based on a ratio relationship. So this is why we can write it into 1, or we can write the total volume if we say that V equals to 1. Of course, now the void ratio If so, if we write weight equals to 1, void ratio is not easy to derive because void ratio is E. So now we ask that equals to 1 minus E, right? And we again, we is void ratio. So if you see now we think that weight equals to 1 plus void ratio. If we say weight equals to 1, so no, weight equals to 1, we can't derive a constant value. We can't derive the terms. So what I explain in here, just to let you know, it doesn't matter we use 1 or 10 or any other number in here, or you can use Vs in here, because the void ratio, it is a ratio in here. If you increase your Vs, your VV also increase, because the ratio never change. So we use 1 to simple the derivation steps. This is the purpose we use 1. If we think this is a unit, so then the volume of voids is right void ratio. So this will simple the derivation step. It's not mean that Vs always equals to E. We think it's 1. It's just for easy derivation of all the relationship. Right. So if Vs equals to 1, then from here, so VV equals to void ratio, so the total volume is 1 plus void ratio, right? And we have this. It's easy. This one, this is definition for specific gravity, right? As long as you know water, unit weight of water, then the products of specific gravity and unit weight of water is the weight of solids. As I said, specific gravity, it is actually how times of the weight of solids or the weight of the material you learn to compare to the weight of water, right? So this is Ws. This is what we learn in here. And from here to here, again, we have this, because gamma W, we think gamma W is 1. All right, yes. Why is this? Because this is a volume, the products of volume and unit weight, right? Because now the weight of the volume equals to E. Then the weight of water equals to the unit weight of water. Multiply the weight, the volume of water, that is void ratio.